Oh, the true proportion of heads for a fair coin is 0.73. Let's evaluate this claim right here. All right, so we are going to evaluate this by flipping some coins. We flipped 46 coins, and we got a statistic of 0.652. Now the question is, how far away from the claim is this? Is it far enough away to reject the null hypothesis? Well, what we want to do is standardize our statistic. We want to standardize our p-hat. Our p-hat is 0.65. This is a z-score of negative 1.2. In other words, the sample proportion of 0.652 is 1.2 standard errors below 0.73. We know if the true proportion is 0.73, we'll not always sample and get something right at the true percentage. Usually we'll be around that. Now, how far away was our sample proportion, these 46 coins where we saw 30 heads? How far away was this? And that answer is 1.2 standard deviations or standard errors. So the question is now, how should we set up our hypothesis test? So here's what a two-tailed test would look like. Here's what a one-tailed test would look like, and the other one-tailed test. So there's basically three choices here. We can have a left tail, a two-tail, or a right tail. Now, two of these tests make sense. The other one is completely crazy. It doesn't make any sense, and we'll hopefully see why that is. Let's first look at the two-tailed test. So the two-tailed test means that we're testing either for less or more. Basically, we're taking into account the sampling variability of the p-hat, the sample proportion, and we're jamming our alpha, or type 1 error, on both sides. Okay. Here what we see is that the p-value is the probability of getting a statistic as extreme or more extreme than the one we got in the direction of the alternative hypothesis. Because we have a two-tailed test, all a two-tailed test means is that we need more evidence, and we need to capture area on the left and capture area on the right. When you do this, you get 0.2301 as the probability. For the left-tailed test, we get half that value. We get 0.1112. So here we have a p-value of, our p-value here is the area to the left of a z-score of negative 1.2. It's worth noting here as well that you can get confusing with all the p's, right? We have p value, we have another p, right? So if we're talking about the p in the left-tailed test, that's just a symbol representing a true percentage, the parameter. The p-value stands for probability, and then the p down below that stands for just the probability of specifically what we're interested in knowing about, and that's the p-value. Okay, so in this one we have a p-value of 0.1112. In either case, consider at alpha of 0.05 what our decision would be. Right, we would fail to reject the null hypothesis because neither of these p-values are below alpha. And the same thing with the third one, which is totally a crazy p-value. Let's see what it says here. It says that the area to the right of a negative z-score of negative 1.2 is 0.8849. Consider, what does this indicate? Why is this such a crazy p-value, and why do we end up with such a big number? Well, we were looking for evidence of greater than 73%, yet our sample was less than 73%. It's very hard to demonstrate more than 73% when our sample is not even more than 73%. So what the p-value here is basically telling you is that you pretty frequently get what you got if the null hypothesis is true. So we're not going to reject the null hypothesis here either. Okay. Now, backing up here for a moment, let's think about why we're not going to reject the null hypothesis. Well, if we reject the null hypothesis, for argument's sake, let's look at just the left-tailed test. All right. If we reject the null hypothesis here, we can't guarantee that we'll be committing a type 1 error less than 5% of the time. So we don't reject the null hypothesis. That's all the alpha and p-value relationship tells us, is if your p-value is less than alpha, you reject the null hypothesis. If it's not, you don't. Now, what does it mean here to not reject the null hypothesis? Some people think it means that you've proven the null hypothesis is true. Notice in this case, we're not proving we don't have enough evidence to reject the null hypothesis. But this doesn't mean, of course, that the null hypothesis is true. It doesn't mean that we've proven that the true percentage is 73%. We never actually prove somebody completely innocent. We just don't have enough evidence to convict that 73% of being wrong. But it doesn't mean that it's right.